Good evening, sir.
Good evening, sir. Sir, my voice is audible, sir.
Yes, sir. It's
yes, sir.
How are you, sir?
Sir, fine, sir. Fine, sir.
Fine.
Sir.
Okay, sir.
Sir, we are very happy to take a resource person today
Thank
for
you, sir.
this
Thank you.
For this faculty development program, sir. Thank you very much for spending your. We are awaiting for your wonderful deliverables.
Yes, sir. Sure, sir. I'll try my best.
Faculty development program.
Sure.
Thank you, sir. Thank you very much,
Okay,
sir.
sir. Thank you.
Thank you, sir. Ma Ritika.
Yes, sir.
Ritika, kindly introduce our eminent resource person who is from Amrita Vidyapeetham, Amrita University, Chennai.
Yes, sir.
Kindly proceed, ma.
Yes, sir. Good evening, everyone. It gives me an immense pleasure to introduce our esteemed resource person for today's session, Dr. R. Prasanna Kumar, sir. Dr. R. Prasanna Kumar, sir, is an experienced academician with extensive contributions in computer science, focusing on artificial intelligence and quantum machine learning. With 25 years of teaching experience in computer science and engineering, Dr. Kumar, sir, is currently serving as an associate professor and head of student welfare at Amrita Vidyapeetham, Chennai. Dr. Kumar, sir, has successfully guided a PhD scholar and is currently guiding 10 scholars. He holds patents for 3 innovations related to damage assessment in thrust bearings, battery management systems for electric vehicles, and artificial intelligent communication protocols. Dr. Kumar, sir, has authored multiple research papers in reputable journals, focusing on topics like data mining, natural language processing, generative AI, and quantum computing. He has also published in top-tier Q1 journals and has 130 papers to his credit indexed in Scopus with an H index of 30. We are truly honored to have such a distinguished and dedicated academician with us today. Thank you for your presence, sir. On behalf of everyone present here, I extend a very warm and respectful welcome to you, sir. We eagerly look forward to an insightful and enriching session ahead.
Thank you, Ritika.
Yeah. Thank you so much.
Now I'm going to hand over this session Dr. R. Prasanna Kumar, sir, Associate Professor, Department of Computer Engineering from Amrita University, Chennai. Sir, kindly take over the session, sir.
Yeah, thank you, sir. Maybe I'll share my screen and then start the presentation.
Yes, sir.
So maybe with all your permission, I'll just switch off my camera for the audio and video clarity.
Yes, sir. Yes, sir. Sure,
Yeah.
sir.
Okay.
Sure, sir.
So can you see my screen, all of you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir. It is clearly visible, sir.
Okay. Okay, ma'am. So can you see the presentation?
Yes, sir. Yes, sir.
Visible, sir.
Thank you.
Visible, sir. Visible, sir.
It is clearly visible, sir. Please continue, sir.
Yeah, thank you. I just put it in the full screen now. Yes. So welcome all for this wonderful faculty development program on quantum hardware. This session 3 topic is on qubits and superconductors overview. So as introduced by your fellow participant, I'm Dr. Prasanna Kumar. I'm working in Amrita Vidyapeetham, Chennai as an associate professor there in the Department of Computer Science and Engineering. Today, maybe for the next 1.5 hours, I'd like to take you to a wonderful journey of how this quantum actually will take the driving seat in the near future, replacing our classic computers. Okay, so this is a wonderful topic to choose with for a faculty development program, and also if some students are there, it's an area to be watched. Just as all are talking about artificial intelligence, quantum computing is also another technology to watch out, which will be, as I told you, replacing the classical computers, whatever we are using as of now. So for the past 2 decades, there's actually a rapid advancement in this quantum computing with the emergence of a concept called as superconducting qubits. Okay. So yesterday I was watching our NIT professor and he was like kind enough to explain about what is qubit and all, like when compared with the classical systems, which has got only like zeros and ones, 2 bits, whereas there's a third state. So RBV Subramaniam sir explained that in a detailed manner in the yesterday's class. So this quantum computing actually is the backbone for this qubits is the backbone for the quantum systems that we are going to discuss today. So maybe I'll take some 3 examples today with quantum hardware related to IBM, Google, etc. Towards the end, maybe I'll just show the hardware and how it actually looks. So this class basically may be like a computer architecture class. I think most of you might have studied computer architecture during your undergraduate or PG course, right? So they might have introduced you about what is a bit, like 0 and 1 bytes, word, and then instructions, instruction set, and then a small hardware, maybe an Intel hardware, Intel 8085 or Motorola 68000 series, etc. So this class will be very similar to that. So you should think about like attending a computer architecture class now. Okay, so it will basically ease out things to you. So as we all know that in the classical system, information is stored in the form of bits, 0 or 1, right? But quantum computers uses a different concept. We call it as qubits. Okay, so this QU represents quantum bits here. So what is the speciality? So it was very nicely explained yesterday by our professor with that cat example, right? The cat test. So a cat was put into a box, and whether it is dead or alive. So it may be either dead or alive. So similarly here also, 0 is there, 1 is there, and the third one, the qubit, is nothing but 0 and 1 at the same time, right? So how much proposition is there? We call this as a property of superposition. Okay, you just remember this word, superposition. So it's a third state, like it can exist both as 0 and 1. So with the third one emerging out, oh, I have shared the screen. Is it not visible?
Sir, it's
So
visible. Visible, sir.
Yeah, so the entire screen, I have that first slide, right?
Yes, sir.
Yeah, okay. Your screen sharing is paused.
Sir,
How can you see me?
yes, sir. Okay, sir. Okay, sir.
Okay.
Now it is clearly visible. It is, I think it is perfect.
Okay. Just let me know in the chat. I think I can see that. Okay. Not visible again. Okay. Fine. So now the agenda, I think now it's visible, right? I moved to the second slide.
Yes, sir. Visible.
Okay, thank you, Ashish. Yeah. So the agenda for today's thing is like introduction to quantum computing, which I was doing a bit, and then we'll go for the quantum hardware basics. Like you know how computer architecture is taught, right? They start with teaching you about gates, like AND gate, OR gate, NOR gate, NAND gate, and using those gates, they will build smaller circuits like sequential circuits and parallel circuits. From those circuits, they'll try to solve some logic, that we use some proportional logic, etc., and we try to solve them. We use tautology, some basic blocks. From those basic blocks, we will be building over to the ALU, right? So similarly, we will be discussing about the basics of computer hardware, particularly related to quantum. And then maybe another bit of introduction to these qubits again we will have. And in addition to that, relevant to today's topic, we will be discussing about a concept called as superconducting qubits. So what is the superconducting qubits? So this superconducting qubits is a form of qubits which generally is used in most of the hardware, quantum hardware now. So, okay, qubits is there, quantum hardware is there, everything is fine. Now, what makes people to still stick on to this classic computers when a quantum hardware which has got a huge computational power to deliver is still not in use? So there are certain challenges. We will be discussing about the challenges in this class today. And of course, we'll be discussing about the applications in cryptography and autonomous system, particularly in how it is used in warfare, a small introduction. And at the end of this presentation, we have, as I told you, 3 hardware we will be discussing, one from IBM, Google, etc. Right? Okay. So that's what I have mentioned as industry roadmap. Now, this is the classical versus quantum computing. This is a small diagrammatic representation. So you can see here like the classical computer. Can you see my mouse pointer, all of you?
Yes, sir. It is visible, sir. It is clearly visible.
Yeah. So the classical computers are there. You can see the bits either represents 0 or 1. So it has got only 2 states. Whereas you can see how a qubit is generated. You all know that I think yesterday's Subramaniam sir was just showing this diagram of a qubit, right? So can someone tell me like what was the name of that sphere called as? This particular sphere is a sphere, right? What is it called as? Someone can tell me?
Quantum sphere, sir. Quantum sphere.
Yeah, very good.
Broad sphere.
Yeah. So that's fine. So Bloch sphere is there. So Bloch sphere is used to represent this third state. Instead of 0 and 1, we have this third state. Now you can see like in this diagram at the bottom, qubits are represented. So I think I told you like the concept of superposition, right? So what is superposition? It is the state in which we can have the third one. It is the bit exists as both 0 and 1 at the same time, both alive and dead at the same time, right? So superposition is used here. And another interesting thing is entanglement. So this diagram clearly shows like how this entanglement inference actually happens. So moving to the next slide. So this is another diagram, like a flowchart kind of stuff, where I just wanted to explain to you what will be the basic changes in the coding aspects, right? So here we have on our left the classic computing. So you can see there are 2 major blocks. One is the algorithm, another one is the compiler, right? So what does the algorithm do? Actually, we have a problem to solve, maybe a small problem like factorial. So we write program in the high-level languages. It may be either in C, C++, Java, Pascal, Python, etc., etc. It is given to a compiler or an interpreter. The compiler or the interpreter, what it will do is, it will translate that into machine understandable language, particularly to the binary format, and it gives to the hardware. Am I right? I think this is a very clear flowchart and all of you are quite aware of it. Okay. Coming to the right-hand side where we have our quantum computing flowchart. So what we do here is, you can see that the topmost layer is almost the same, right? So there's a problem to solve, the same, like factorial problem is there. We have an algorithm. So we are not going to write a program in C++ or Java here, but we have to design a parametric quantum circuit. This is quite interesting. So we have tools like Qiskit, which can do this job. So Qiskit is a Python-based tool. Anyone aware of this? Have you heard about what is Qiskit?
This means it contains zero also. The figure of this contains
QISKIT, right? So it is like an open source program. Basically, it is from IBM actually. It is only meant for quantum computing. Okay, so what Qiskit will do is, it will be helpful to create quantum circuits. Please understand that we are not going to write a program here with the algorithms. You know what is an algorithm, right? So maybe like there are n number of algorithms, algorithmic techniques and all we might have studied. Dynamic programming, divide and conquer algorithm, etc., etc. So here, the same algorithms, what we do is we have to design parametric quantum circuit. Okay, just like using tools like Qiskit. So we have a transpiler, like instead of a compiler, we have a transpiler here. It will optimize these quantum circuits, and then you can see the compiler over here. So it is to compile for the hardware. See, quantum hardware, there are different types. Maybe I'll just show, I'll be showing them. Okay, so the circuits, whatever is designed over here with the tools like Qiskit will be given to this compiler for, the compiler will compile for the specific hardware. And then we have this optimizer, and this optimizer will be given for execution. Okay, so here there are two things you can see here, whether it is converged. If it is converged, then it is considered as a solution. If no, it will again go to the optimization phase, and then this I'm sorry, this particular loop will continue. Okay, so here, do you understand the difference between classic computing and quantum computing?
Yes, sir.
Yeah.
Sorry for interrupt. Can I
No, I can't get you. Sorry for interrupt. I heard clearly, but after that, I was not able to hear.
Yes, sir.
sorry, sir.
Sir, here,
Sir,
please,
how
sir, please explain. No and yes, sir. Up to there, everything is clear, sir.
Okay, here, this convergence, right? Fine. See, we design a circuit. The compiler actually creates the compiled code so that the quantum system can handle it. So we have a quantum optimizer that can optimize. Generally in Qiskit, like for this optimization job, we use a concept called as transpiler, TRANSPILER. The transpiler will do this classical optimization. Okay, why do we need classical optimization? This optimization is to map whatever circuits we have designed to that of the physical quantum hardware. It will be like mapping the circuits we have designed using tool so that it can be given to the actual quantum hardware to get worked. Okay. So actually what we do here is we have some quantum pre-built libraries which can be used to do this. And here the execution actually is done. So here you can see that the parameters are passed over here. When the parameters are passed over here, Ravindra Reddy, please wait. I'll just take into that. Yeah, you have a good question, but let me just move to that slide. Okay. So is there any specific algorithm? Yeah, I'll just explain. Maybe I can show at the end a small code. If possible, I'll just show it. Okay, don't worry. So we'll be executing using the hardware, and we'll be getting some probabilistic outputs. It will give some random outputs. So those outputs will be evaluated. If we feel that the output is correct, if yes, you can see, then it is considered as the solution. And if we feel that it is not converged yet, again, it is given for re-execution, and it will keep on like what we do in machine learning. The same thing happens over here. Okay, fine. Now, this is the history. I don't want to take much time. Maybe I have shared this presentation in the PDF format. I'm sorry. As well as in the Canva format to your coordinator. Maybe you can just get it off from him, and you can have a look at this history, right? So it started in 1900, way back, some 125 years back. Planck's quantum hypothesis was the base for that. The major breakthrough, I think you might have heard from yesterday's talk, is in 1994 by this Shaw's algorithm and Brewer. So these two algorithms, 1994, played a major role. And then, of course, we have another breakthrough in 1996 by DeVincenzo. It's actually another wonderful thing. And from 2000 onwards, work was going on. Okay, so this is a roadmap. And maybe you can see big companies like Microsoft, they have a quantum machine from 2016. It's called as, I'm sorry. Yeah. So it's called as Microsoft Station Q, and we have from Google, Google Quantum Supremacy, and IBM. So these are the three examples. Maybe I'll be just explaining at the end also IBM Quantum Roadmap. So these are the things. And of course, like you can have a number of other advancements also. Now coming to the next thing, like this is also a kind of same presentation, but it has a little bit of mathematics inserted. You can see here like how this spheres are considered and how quantum mechanics actually evolved and all. So maybe you can have a look at this history kind of stuff later. These timelines are just for your information. Now, coming to the quantum hardware, you can see one nice picture of a quantum machine over here. This is not like the normal system that we use. Okay, so I'll be teaching about in this section. So this section is about the quantum hardware. Here, what we are going to discuss is about the physical foundation of these quantum computers. So how these quantum computers will look. You can see a number of wires, circles, rings, etc. here, right? Can you see that nice diagram over here? This is a quantum computer, okay? So what is the physical foundation? Just like, see, a classic computer, I can see even my mobile is a classic computer, right? It has got a CPU, GPU, etc., etc. Give some problem to it, it can solve, and I can see whatever it is. But what is this quantum hardware and how it will look? Okay, in India, is there quantum computers? Yes, one or two computers are available in India also. CDAC has one quantum computer in Bangalore, I know that. Others, I don't know about the private industry, but one is with the government of India. Right, so how this quantum hardware will actually look. So we'll be describing or explaining about what is qubit, how the control system actually works over here. And there are, of course, a number of measurement devices which are used here. And we'll be discussing about superposition. I think we have I have introduced what is superposition, but we'll be explaining that about in a detailed manner. Entanglement, measurement of computation, what we do. And of course, like for a quantum computer, it requires a special infrastructure. We cannot just like that carry as we carry our laptop everywhere. Okay, so it requires a concept called as cryogenic setup. What is this cryogenic? Have you heard about this word cryogenic? Anyone?
Cryogenic engine for satellites, rockets launching, sir.
Very good. Ashish has answered like cool. Yeah, of course. Cryogenic is nothing but sub-zero temperatures. So the temperature should be maintained at 0 degrees, right? Very good. So cryogenic engines we use in rocket, right? They say that. So what is this cryogenic engines? Actually, the fuel is, what is it? It's almost, the fuel will be set to 0 degrees Celsius. And as the rocket launches up, it just gets fired and the fuel will be utilized by the rocket. So for a quantum computer, this cryogenic setup, which is required to maintain the machine at 0 degrees Celsius is required. Okay, and then second one is the error controlled mechanisms for stability. Why stability is required? See, we saw that one sphere was there, one arrow mark was there. Am I right? Maybe I can just move out. So you can see this arrow mark. When it moves up, we say that it's a 0, and when it comes up, it's a 1. And it can be either in the 0 or 1 state, right? So here stability becomes a problem. Okay, so we need some error control mechanism for stably maintaining either this a 0, 1 or in both the states. So these are the two special requirements. One is the cryogenic setup, and also safety for liquid helium. Okay, good. Ashish, I think you're very active. Nice. And error control mechanisms are used here. Now, here comes the hardware stack. You know what is a stack? Am I right? I think we might have studied about stack in data structures. Okay. Now, here is the quantum stack. At the bottom, that is the blue color thing, you can see that I have marked it as the quantum plane, also called as topological qubits. So what is this topological qubits actually? So this is the foundation. If position, please, stack follow first in, first out. Yeah, good. Okay. So this topological qubits actually forms the classical stack of a quantum machine. So what it actually does, it's also called as the quantum plane. Okay. So the real quantum computing actually works over here. This blue color actually has what we were talking, no, the qubits and all. So the physical bits, they actually exist in this topological qubits. This is the bottom layer. So the physical bits exist in this in multiple states. You know what is multiple state, right? 0, 1 or both the states. So the okay, stack is last in first out. Yeah, of course. Okay. Oh, previously it was FIFO. Okay, I was concentrating on the topic. Fine. So here at the bottom, the topological qubits, here we have this qubits there. So what happens over here is due to the superposition and entanglement, these states are maintained. Okay, that's a very interesting thing. We can call that the entire hero of this movie, this quantum computer, is this blue color box at the bottom. Okay, so all the above are just helping this topological qubits to work. Okay, so they are really very special because one interesting and important property of this qubits is that they are resistant to noise and error. This is very important, which makes quantum computer very interesting concept for application, particularly in cryptography, cyber security and all. Okay, so it gives basically a platform, a computation platform that is more stable. That's very important. It gives us a stable platform, which means that the system is very stable in this bottom layer, the topological qubits. Above that, there's a green color box. Can someone tell me what is that? The cryogenic control. So there are two things over there marked in green color. One is cryogenic control. Another one is room temperature control. So this is the interface actually. Okay, this is the interface. The cryogenic control actually controls the temperature of the topological qubits. It maintains that 0 degrees. Okay, it maintains that 0 degree. So above that, you can see the room temperature control, which will try to maintain the room temperature, maybe 25 degrees, 26 degrees, some 30 degrees, etc. Okay, why do we need this cryogenic control? I told that qubits are resistant to noise and error, but at the same time, qubits are very much sensitive. They are very, very sensitive. So they must operate this. Qubits should be maintained, or they must be operated at near 0 temperature. So the temperature should be maintained at 0, and this cryogenic control is in charge for maintaining this. Okay, so what will happen if you're not maintaining that? This topological qubits will get disturbed due to external temperature, and it may not work properly. So we need this cryogenic control for maintaining the temperature. And above that, you see the room temperature control. We can call them as the translators also. What is it translating? See, when you enter this cryogenic area, it will be 0. Just move outside of that, you will feel the room temperature. Okay. So here above that, you can see one yellow color box. What is it? The classical computer. What is this classical computer? The classical computers are the one. This is, see, I'm using a laptop and I'm just presenting this. No, this is a classical computer. So it will have applications, solutions, software, blah, 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 etc. Okay, this is an interface between a quantum computer and a classical computer. So the quantum computer actually ends with this room temperature control. You can see that the quantum classical interface helps in doing this. The classical interface has got two things. One is the room temperature control, another one is the cryogenic control. Now there are, you can see some interesting features, right? Two types of arrow marks are there. You can see here, one is high speed digital. What is this high speed digital? See, these are the signals, these are the digital signals that are passed to the classical computer and from the classical computer. You all know that our classical computers are digital systems and which operates on zeros and ones alone. Am I right? So this particular arrow mark, you can see this like here on the left hand side, you can see they are high speed digital data transferred. You can see in both the directions data is transferred. And you can see a small blue color arrow mark, which are nothing but the analog signals. See, the quantum computer works in an analog manner, not in digital as in the classical computers. That's one advantage of quantum computing. So you can see that this arrow marks, you can see it moves inside and also it moves outside. So whenever a signal comes out of the quantum computing, will it be a digital or an analog signal? Can anyone answer in the chat? I'll repeat the question. When some signal comes out of the quantum computing, very good, it's analog. So the input is also analog. What about a digital, what about a classical computer? It will be digital. Okay, yeah, Kavita has answered that, good. So do you understand this stack, all of you? Yeah, the street, fine. Ravindra Reddy, good. Okay, so you understand how the information flow actually happens? Good. So it happens in a hybrid mode where digital as well as analog transmission happens. Analog transmission happens within the quantum computing, and when we need to use the classical computers, we need digital signals to be used. Okay, fine. So this particular slide, I think yesterday I was attending the full session and I was listening to Sir's thing. So he was explaining about this qubit, right? So what is this power of qubit? That's very interesting, right? So it's not alone superposition. What is superposition? At any given point of time, it can maintain either in a zero state or a one state, like the cat is dead or alive, right? You have to remember that example. Inside the box, till I open the box, this cat can be either dead or alive. In both states, it will be dead, right? Okay. So the power of qubit is that it's not only superposition, but we can go for entanglement. What is this entanglement? The qubits become interconnected. That's very important. Okay. So what is the use of this interconnectedness? The qubits become interconnected in ways that allow the measurement of one qubit. Okay, correlated to each other. Fine, good. Measurement of one qubit to instantaneously affect the other. That is, one qubit can have an impact on the other regardless of the physical distance. That's very important. There's no relationship between the distance and the impact or the interconnection between qubits. So this particular mechanical property of qubits actually enables quantum algorithms to solve specific problems faster in the sense exponentially faster. You know how, what is exponential growth? Am I right? We study that in algorithms, right? Exponential growth should not be there, particularly in terms of time. Rapid growth, very good, Ravindra Reddy. So it should not be exponentially faster. If it is, it should be exponentially faster so that we can solve the problems in a easy manner. Okay, so where it is applied? It is applied in areas like cryptography, optimization techniques, and particularly in biosciences like molecular simulations, etc. Okay, fine. So now I think there's another slide which talks about the building blocks. So you can see the Bloch sphere here, BLOCH. Am I right? The Bloch sphere is over here, and it is a 3D globe-like structure, right? Yes or no? Now, maybe I can just zoom this diagram. Can you see the zoomed on?
Yes, sir.
Yeah, good. So here on the top of it, okay, you can see like 0. Am I right? So there is a symbol, 0 is embedded within a symbol. Can anyone tell me what is that? Thank you, Nagendra sir, Dr. Nagendra. Yeah. Can you tell me what is the name of that? There's one line and then one greater than symbol. What is it called as? It's called as? Okay, Kit. And that greater symbol is called as Ashish. Yeah, good. Bra, good. So, yeah, it's a bracket basically, right? BRAKET. That's all. Okay, Kit and bra, bracket in 2 parts. Very good. So we have the 0 over here and we have the 1 at the bottom. Am I right? But you can see in between there are certain states. So we have like 2 things. One is theta and another one is phi. I think yesterday professor was explaining about them in a very detailed manner. So at the top we have like complete 0. At the bottom we have complete 1. And in between there's a thing called as an equator, right? So this is the equator is the place where the qubit is off 0 and off 1. Okay. So it's not 0.5, it's off 0 and off 1. This is what we call it as the superposition state. Okay, the equator state. And then we have a state arrow. So the state arrow actually is line from the center. If I can just point out to this center, the line from this center to any point of the sphere, we call it as the state arrow. And then we have these angles like you can see theta and phi. So these angles describe how much the qubit is in 0 or 1. Since it can be in 0 and 1, so it will tell how much 1 and how much 0 it is. And what is its phase, okay, the direction of rotation, etc. So I think this is a small introduction about the qubits. So these are the basic building block, like how 0 and 1. You know, I think they will put a signal, right? Do you remember? Analog signal means they'll put a sine curve. And for a digital signal, they'll put like a steps. Am I right? Similarly, quantum computing, the basic building block is this qubit. It is represented by blocks. This block is called as Bloch sphere. Okay, fine. So a more detailed manner of this is mentioned over here. Maybe you can refer it for future things. Now, there are certain components of this Bloch sphere. I think I explained about that. There are 6 components, I can say. One is the qubit state, like 0, 1. And I think these formulas and all yesterday professor was explaining. And we have this axis X, Y, and Z. So what is this axis is X, Y, and Z? So these are the reference lines, basically. They show how quantum gates move, right? So we use the gates, a kind of gates here, and these gates are called as quantum gates, okay? So how these quantum gates actually move. It is like rotating around the x and y axis, x and z axis, etc. Okay, so all these mathematical representations are given here, and then of course the angles theta and phi. Okay, so now since it's about the hardware, what are the types of qubits? Okay, so different companies have their own different qubits representations. Maybe I can move on to this. So these are the different hardware part of the qubit. You can see one is superconducting qubits, trapped ion qubits, spin qubits. Can you go back to the previous slide? Yeah, I'm just showing this diagram. Bhagyasri, good. I'll go back in the sense you want that qubit representation or this one types. Okay, I'll just explain that. I'll go back to it. But anyway, just for our understanding, I'm just moved here. So there's another thing called as topological qubits, photonic qubits, neutral atom qubits. So there are different qubits available. Okay, components you want? Okay, Bhagyashree, yeah. Any question from here?
No, sir, no question.
Okay, fine. So here, I've showed their significance difference based on hardware classification. Yeah, there are differences. Okay, Ashish, yeah. So here, what is this superconducting qubits? So it is made of some tiny circuits, okay, electronic circuits. They conduct electricity without resistance. Resistance equal to zero. We all know that V equal to IR, right? A basic formula where voltage is directly proportional to the uh, what is it, resistance, right? So the superconducting qubits actually conduct electricity without resistance. When there's a condition here, it will not be conducting always with zero resistance. It will be conducting with zero resistance when cooled to very low temperature, particularly like 0 degree. That's why that cryogenic temperature, you can see circuits at cryogenic temperature. So two companies, IBM and Google, actually uses this type of qubits. So they have quantum computers where they maintain this cryogenic temperature. They use superconducting qubits. Okay, and then there's another company called as IonQ. You can see here, IonQ uses a kind of qubit called as trapped ion qubit. You know what is an ion, right? Can anyone tell me what is an ion?
Charged atom is ion, sir.
Yeah, charged atom. Very good. Ashish, good. So charged atoms are called as ions. So this company, IonQ, it uses these charged atoms. These are trapped. So the word trapped is used here. Trapped in electrical fields. Okay. Okay. Ions are there. They are surrounded by some electrical field. Who will control that? It will be controlled using laser. Okay. You know what is a laser, right? It's a high intensity focused light, right? So we have this charged atoms, that is ions. Ions will be put inside electrical fields, and these ions will be controlled by using laser. Okay, they are very accurate, but actually when compared with the supercomputing qubits, they are a little bit slow. Okay, so for huge applications, still this trapped ion qubits are not recommended. Now coming to our major software giant, we all use Windows, right? Microsoft. So what Microsoft uses? So Microsoft has designed a special qubit called as topological qubit. You can see here, right? The third one. So this topological qubit is like, it's a futuristic qubit. Okay. So Microsoft claims that they are more stable and they are very, very less affected by noise or external errors. Maybe like still people are trying to understand how this Microsoft has come out with this topological qubits. No much data is present in the outside world. Only thing is that this is robust and error resistance. Not much about how it works is available in the public domain. And two more companies, Zandu and PsiQuantum, you can see here. Zandu and PsiQuantum, they have designed one type of qubits called as photonic qubits. You know what is photons, right? Photons are particles of light. Very good. So they use like particles of light, these photons, to carry information. Very good. So actually the name is Dell. I don't know what is the name of the user. Maybe the laptop name. Fine. Yeah, positive energy. Ravindra Reddy. Good. So this photonic qubits actually uses photons to carry information. They actually work very good for sending quantum data for long distances. This photonic qubits. Okay, and there's another qubit called as spin qubits also. They are like made with silica or diamond actually to represent these quantum states. So these are the major types. So these are the physical types, like how it will look. You can see this spin qubit here, right? So spin qubit actually, it uses spin of electrons. Basic electrons are atoms. And as I told you, they are made up of diamond to represent the quantum states. Okay. So this is how a qubit will look physically, the hardware of the quantum qubit. Now we'll move on to the next thing, superconducting qubits. So it's very important since data is to be transmitted or information is to be transmitted from one place to another. So we need conduction. So superconducting qubits in quantum hardware. So what is the basic building block of a quantum hardware? Qubits. There are different types of qubits. You can see those types here. Am I right? Shall we move to the next one? Any questions till now? Okay, that's fine. So coming to this particular topic or the next topic in discussion. So the superconducting qubits are nothing but quantum bits, which we have seen already. They are made from superconducting circuits. Okay, so they use a kind of junctions called as Josephson junction. Okay, and these operate at cryogenic temperature, that is sub-zero temperatures. It helps for superposition and entanglement. I think we have discussed about what is superposition and what is entanglement, right? So actually the superconducting qubits utilize the superconducting circuits. We all know that they are very small electronic circuits. They operate at sub-zero temperatures. It is used to create artificial quantum systems which can be controlled by us. Okay. So what is this artificial quantum systems? It's nothing but the artificial atoms. Okay. So these artificial atoms are engineered using superconducting materials. I think the commonly used material is aluminum. I think we all know what is aluminum. Am I right? In day-to-day life also we use aluminum, and sometimes they use another material called as niobium, Niobium. Okay, instead of aluminum sometimes they use niobium. So why do they use these two? Can someone tell me? Why do they select aluminum or niobium for this? Okay, Kavita, lightweight, that's good. Ashish, that's why planes made aluminum as so fast. Okay, fine. That's not the answer. Someone else can try. Do you remember I was using a word called as zero electrical resistance?
This aluminum material is always attracted to the positive energy.
Okay, they are lightweight, that's okay, and they are abundantly available. That's the second thing. Third one is this aluminum or niobium, actually they exhibit zero electrical resistance. So I think I told you that it should have zero resistance at this cryogenic temperature. Okay, so people prefer this aluminum. Okay, so anyway, they use this Josephson junction. So this Josephson junction is a quantum device. It has two superconductors. How many superconductors are there? It has got two superconductors. They are separated by a thin insulator. Okay, good for error control. Yeah, error control actually it will come when we can be able to maintain that zero resistance, right? Good. So coming to this Josephson junction, it's a junction. Junction means you know that some two places will be here, right? So it consists of two superconductors. These two superconductors are separated by a thin insulating barrier. So one insulating barrier will be there between these two superconductors. So this barrier, actually, this a wall-like structure allows the Cooper pairs of electrons to give this quantum mechanical effect. So what it will do is it will create a nonlinear behavior essential for qubit operations. Okay, it's a bit of tricky thing, but don't worry about this. So as of now, just understand how actually this works. So here, like this is a slide which explains to you about superconducting qubits. So what are there? What is the first one? You can see there are 4 types listed over here. What is the first one? Yeah, phase, PHASE. So phase qubit. Next one is flux. Third one is charged qubit, and the final one is cat qubit. Now coming to this first one, phase qubit. So what does this actually work? So this operates by controlling the phase difference. What is phase difference? Do you know what is a phase? Phase difference? I think you might have studied some electrical engineering and all. 3-phase supply in very good angle. Yeah. So maybe like the difference between sine and cos. What is the angle difference? Sine and cos?
90.
Yeah, very good. So coming to this phase difference, this particular phase qubits operate by controlling the phase difference across this Josephson junction. So Josephson junction has got 2 superconductors, and between this it has got a a wall-like structure. Okay, so this qubits actually use the harmonic energy level. So that's very important. It uses the harmonic energy levels of the junctions to create a controllable 2-level system. Okay, so it uses the phase difference. Now coming to the second one, like this one, the flux qubit. What happens to the flux qubit? So this qubits, you can see there's a inductor kind of stuff over here, some resistance here, and then we have this what is it, entangled qubit here. So the flux qubits actually encode the quantum information in the direction of the current flow. Okay, so which direction the current actually flows through the superconductor, particularly with that Josephson junction, the encoding will happen. So the quantum superposition exists between the clockwise as well as anti-clockwise current states. It's based upon in which direction the current actually flows. So this is another bit of flux qubit that can be used. And you can see like at the bottom for phase qubit, actually, so 0 and 1 qubits are there, 2 energy levels, and it uses microwaves. A resonator and microwaves are here used, and no one uses this phase qubit now. You can see the word abandoned, right? Whereas if you go for this flux qubit, it uses like 2 superconducting current directions, as I told you, clockwise as well as anti-clockwise. It uses some magnetic fields, and the qubits is read using magnetometer. And companies like D-Wave, Rigetti, and all these things use this type of flux qubits. But anyway, you can see here the basic thing is the Josephson junction. Okay, it is used to handle the qubit degree of liberty over here. Coming to the third one, we have this charged. Why it is abandoned? Okay, maybe due to its like efficiency and like the hardware support required for that. They might have abandoned it, but I'm not sure about the exact reason. Okay, I'm sorry. So coming to the charged qubit, how it actually works. So the charged qubit actually works in a manner like you can see there is a capacitor used. I think we all know that the 3 passive components, right? Inductor, resistance, and capacitance. So it uses this concept over like charging. So here you can see charge. I think we all know that capacitors are used for charging. Am I right? Do you remember that? Farads, right? Okay. So charged qubit, it uses capacitor instead of an inductor like here. And it uses 2 levels of charge of these Cooper pairs and microwaves. Here we are not using magnetic field, but we use microwaves here. And resonator and microwaves are used for this readout. IBM, Google, all these things uses this charged qubit method. Okay. And then of course at the last, we have like the Josephson junction couple and correct the CAD qubits. We have this CAD qubits here, which is used by Amazon. Amazon quantum computer uses this method called as CAD qubit. Okay, So what it does is it has a pair of entangled microwave photons in a cavity. So a small cavity is made, and a pair of entangled microwaves are there, and based on the resonator and microwaves, this qubit actually works. And this is a self-explanatory. Okay, okay here. So superconducting quantum computing system. So what is at the bottom is the physical quantum processor. So what is this physical quantum processor? It will have that qubits, blah, 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 there it will be there. And we have the readout and control. So the readout is like the quantum limited amplifiers, and controls are microwave pulses. And along with that, we have the quantum error correction. All these three actually forms the physical layer. Okay, the physical layer of the superconducting quantum system consists of the physical quantum processor, controls, readout, and the quantum error correction. Above that physical layer, we have the logic layer. We all know that, right? A computer is, it consists of two things. One is the physical layer, another one is the logical part. Logical part is nothing but the programming part, physical part is the hardware part, etc. Blah, 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 right? Same thing is explained over here. Okay, so what is readout? It's a good question actually. So see, okay, Ravindra Reddy says that my voice is not audible. Can anyone confirm that? Am I not audible?
Audible, sir.
Yeah, okay, thank you. So what is this readout? A question from one of the participant. So readout in quantum is nothing but it is used to process the final state of the quantum qubit. You can see that the quantum limited amplifiers are used here. So the qubit's final state, see, we know that it may be either 0, 1 or in both the states. So this readout will be measuring the final state after computation. Okay, once this physical processor computes something, and once the process is over, this readout will check what is the state of this quantum computation. Okay, so what is the need for it? Yeah, it is measurement, of course, obviously. Yeah. Okay, I'm sorry. So it is very much required for detecting a change in the electrical properties. You know that this is basically an electrical based thing, and we should be knowing about the changes that happens over here. Okay. We have the control over here, like controls. It uses microwave pulses. You can see over here, it uses the microwave pulses. We can move, so what we can do is we can move the qubit between these energy levels. It is used for creating the superposition or entangled qubits. Okay, fine. So this is the basic architectural diagram. And then above this, you have the quantum algorithms like Shor's Gross. I think there's a separate session for that. I saw in your schedule. Okay, maybe 7th or 8th session, they'll be talking about these two algorithms and how it actually works. Fine. So why supercomputers is required? That's a very important and interesting question, right? So we all know that the Josephson junction, it consists of two supercomputers. Two superconductors separated by a barrier, right? So we are discussing about that. So why we need that? First one is zero electrical resistance at cryogenic temperatures, that is sub-zero temperatures. The resistance will become zero. This is point number one. And then the next point is it will enable tandem quantum coherence, okay, with minimal energy loss. So that's why we go for this superconductors. And also it is very easy integrating the microcircuits for scalable processes. You know what is scalability, right? So we all need the scalable system, since we don't know like how much of data we have to process or how much information we need to process, and hence scalability is very much required. And the fourth property why superconductors are used in this quantum computers, or that they are they are like ultra fast materials for gate operations. You know what is gate, right? NAND gate, AND gate, and all, right? So this superconductor support ultra-fast gate operations, which is the backbone for this quantum algorithm. So these are the 4 reasons why superconductors are used. Okay. And then coming to our concept, Josephson junction. I told that 2 superconductor, 1 insulator in the middle. You can see the diagram which is on the right hand side, right? So if I want to build 1 qubit, I need 1 circuit like this, which is called as the Josephson junction. Okay, so a thin insulator is sandwiched between the 2 superconductors. You can see over here. Okay, so and how it actually works. It behaves as a nonlinear inductor here, which enables the quantum behavior. That is, it allows the system to be in state 0 as well as in state 1. So it is, as I told you, constructed with 2 superconductors separated by a thin insulated barrier. In between, on the right hand side, there's a word called as Cooper pair. Okay, so what is this Cooper pair? These are pairs of electrons. Okay, I repeat again, this Cooper pairs, you can see that electrons minus symbol, you can see 2 electrons, right? So pair of electrons, they are bounded together. You can see that these 2 electrons here, okay, are bounded or together by an attractive force at low temperature, particularly during this cryogenic temperatures. Okay, so and also it will have that 0 electrical resistance, which enables superconductivity. Okay, so this Cooper pair is nothing but a pair of electrons. So they are together by an attractive force at low temperature, particularly at 0 temperatures. Any questions on this?
Sir, Cooper pair forms with 1 positive and 1 negative electron. Both negative.
So electrons basically are negative, sir.
Negative.
Yeah.
Okay. Okay, sir.
No, in a basic atom, electrons are like negative things, no?
Okay, sir. So attractive force between these 2.
No, that's what. These negatively charged subatomic particles are bounded by using this low temperature, 0 temperature.
Okay, sir. Okay.
That is called as Cooper pair.
Okay, sir.
I think protons are positive charged, right, in an atom.
Yes.
Okay.
Yes.
Now, this Josephson circuit, it has got 3 variations. Okay, the first one is SIS junction, second one is SNS junction, another one is SCS junction. What is this SIS? So S stands for superconductor, no change in it. The first one, I stands for insulator, N stands for normal metal, and C stands for constriction. Okay, so what is this? We'll discuss one by one. So this is taken from a research article. Basically, I have given the reference over here at the bottom. The paper, you just click over this, it will take you to that journal article. You can download that and read. But anyway, I'll be just explaining this one by one. SIS, SNS, and SCS. What is this SIS? SIS stands for superconductor, insulator, and superconductor. Okay. So actually the thickness of the superconductors will be like 1 to 5 nanometers. You just think. Nano means how much? 10 power?
-9.
Yeah, very good. 10 power minus 9, right? Not 9. 10 power minus 9. Okay, good. So we have this 1 nanometer thick insulating barrier. You can see like the qubit chip here, A, B, C, D, 4 diagrams are there. Am I right? So the first one, A represents SIS. Okay. A represents SIS. So it is the superconductor, insulator, superconductor. So the thin barrier, the barrier between is like 1 to 5 nanometers thick. This barrier is made of normally aluminum oxide. Okay. The chemical, or sorry, the element the material used for creating this barrier is aluminum oxide or sometimes magnesium oxide, but maximum they use aluminum oxide only. Sometimes they use magnesium oxide. So what are the properties of this SIS? This is SIS. Basically, you can see here, this is SIS. So what are the properties of this SIS? This SIS actually has the highest critical current density among all these types. The other three are there. One is SIS, SNS, SCS, and there's another one called as pi junction. You can see here the D, okay, which we'll discuss later. So it has got the critical current density highest, and the resistance is also quite normal over here. Where do we use this? We use this in voltage standards, superconducting qubits, etc. The second one, B method. B is nothing but superconductor, normal metal superconductor. So in the first one, we used an insulator, and I told that it will be like, can you tell what material is used as an insulator? Two materials I told. What are they? Yeah. One is aluminum oxide. Another one is magnesium oxide. Am I right? Yeah. So here, coming to this normal metal, can you name some metal? Normal metal. Just guess. The costliest metal. Okay, copper is good. Another one, gold. Very good, Ashish. Yeah. So here, this normal metal is nothing but it's made up of generally gold or copper. They use gold or copper over here between the superconductors. Anyway, two superconductors will be there, no change in it. In between, in the barrier used is not magnesium oxide over here, but it is gold. Okay. So the advantage over here is that it is having very smoother voltage transition. So it is one advantage. So where do they use? They use this in gate controlled quantum devices. Okay, the application for SNS, superconductor, normal metal superconductor type of junction. I think junctions and all you might have studied in electronics, right? PN junction, NPN. Do you remember that?
Yes.
Similar to that, nothing more. Instead of NPN, PN and all, here we use superconductor, one barrier, superconductor. The barrier, if it is aluminum oxide or magnesium oxide, we call it as SIS. In case instead of magnesium or aluminum oxide, we use gold, it becomes SNS. Now, what is this SCS? Constriction. What is this constriction? Constriction is nothing but, can you tell me the meaning for constriction? CONSTRICTION. What is the English meaning? Direct meaning for this? Blocking. Very good. So junction is like a barrier is used for blocking, right? So here, this constriction is nothing but it's a very narrow physical material, okay, which will create micro bridges between these two superconductors. Okay, you can see like number C is an example for that. Okay, and then of course we have the fourth one, which is nothing but pi junctions. At the end, you can see that pi junction qubit. So this actually qubits are you can see there's a junction over here. These junctions, the ground state phase difference equal to pi. Okay, instead of 0, it's not 0 here over here, but it becomes pi here. This is one among the feature of this pi junction qubit. Okay, normally it is used in quantum computing qubits, digital logic circuits, they use this pi junction qubit. Okay. And then of course, like they have another thing called as long Josephson junction, which I think is not that much relevant here. Similar to synaptic gap between neurons. Yeah, Ashish, good. Ashish is moving in a different direction. Really good. Okay, now coming to the challenges in quantum hardware. I think now we have discussed about what is a qubit and different types of qubits and how actually qubits are built by using this Josephson circuit, right? SIS, SNS, etc., etc. Now, we are moving to the next thing. What are the challenges? Why this quantum hardware is still not used very much in public? We all know that we have to maintain that 0 degrees Celsius, which is really difficult. Really difficult in the sense a lot of heat will be produced, and that heat will change the temperature. Maintaining that 0 degree requires huge power. Am I right? Huge electric power. We all know that now AI is using huge electric power, and this also requires huge electric power, right? Okay. So the challenges, you can see that the middle cooling and environmental factors. So we all talk about sustainability nowadays. Like we say that we should be energy conscious, we should use less energy, etc., etc. So whereas this quantum hardware actually it requires huge electric power to keep or maintain that cryogenic temperature. This is one. So we all know that when we want to maintain this, of course, the cost of the qubits creating that, we are using superconductors, we want gold and all, and the cost of gold and all, right? So it becomes very much costlier. The cost and accessibility is another major challenge in quantum hardware. And these are the main thing. Right and left, we have the scalability and error correction. It's somewhat difficult to scale the supercomputers. If I want to scale, I should build a massive hardware. If I build massive hardware, the cost will become exponentially higher. Okay. And coming to this side, the competition among quantum computing companies, as I told you, like Google is building their own thing, IBM their own thing, Microsoft their own thing. So there's no consensus, and each and every one of them are trying to have their own hardware, and they have their own qubits. The method basically differs. You know that one is using a different method now. I think there are. Can you remember like what are the qubit types? Can someone tell me? I showed a diagram also. Okay, Kavita, yeah, good. Trapped ion, superconducting, photonic, spin, topology, etc., etc. Right? So they have their own methods of constructing, which is still a challenge. Okay, do you accept all these four are challenges in this hardware, quantum hardware? Yeah, good. And since we have to maintain this cryogenic thing, the problem is also with the fabrication. We have to fabricate that device, right? So if you want to fabricate a qubit, actually the preciseness and everything, it's really difficult. Even a small, imperfection in that sphere actually will destroy the entire performance, right? So fabrication is still a challenge, even though we have good electronics now. And of course, decoherence is another thing. So when this qubits interact with the normal environment, it will lose its quantum state. Okay, that's a major, the coherence character will be lost, and of course, everything will be lost over there. Okay, fine. So, I think this is self-explanatory. Am I right? Cooling requirements. It need a dilution refrigerator, colder than space. Okay, approximately 15 mK. Can someone tell me what is this 15 mK? Any guesses?
Millikelvin.
Yeah, millikelvin. Okay. Very good. So extremely, so it's extreme and expensive, and large scale integration is really difficult. Okay. And scalability, like creating one qubit itself is a problem, and integrating hundreds of qubits, thousands of qubits, you can see fabrication is a major problem. I think I discussed about this. So fault tolerance is another important thing. We have to protect our qubits from noise. Thousands of physical qubits has to be done. Error correction, hardware engineering is still in its nascent stage. Okay. So what are the applications and futuristic views? Maybe how much time still we have? 15 minutes, right? Okay. So I'll stick on to the time, right? Since the other next session is there to you. So what are the various applications? Like it is very much used in quantum cryptography. I think there was a session yesterday on 5G, 6G quantum cryptography applications, communications, etc. So it is used for secure global communications, underwater secure channels. Since this, what is it, FDP is about underwater device connection also. So quantum cryptography will be of great use. Also, this is used in autonomous systems and cryptography. It enables secure communication through a concept called as quantum key distribution, which is really, really difficult to crack. Okay, so this quantum key distribution, particularly, they are used in vehicular networks. Yeah, Raghunath Reddy sir was explaining about this QKD yesterday. Very good, Ravindra Reddy. Thank you. So, and then we use this in protected. It protects autonomous systems from cyber attacks and eavesdropping. And quantum sensor are used for accurate navigation, particularly in GPS denied environments. Okay, this sensor will be of great use, and it ensures data integrity and trust in underwater and remote missions. And it forms the backbone for quantum secure robotics and autonomous fleets. I think you know what is an autonomous fleet and all, right? They use it in what is it? Logistic environments. Okay, fine. So here you can see like a nice diagram. Am I right? What is it actually? Someone can you just tell? You see the second maybe
But it is running on have networks.
yeah, so quantum drones, am I right? We have some quantum drone network. You can see here high altitude quantum drones, low altitude quantum drones, and we have like quantum communication happening. Ground networks are connected through this optic fiber channels. And this 3-node quantum computers, you can see 1, 2, and 3 nodes are used for communicating. So here, see, this is like a futuristic concept. Okay, it's not presently in use. The source for that, I think you can see at the bottom, sciencedirect.com/that article. So anyway, I shared this presentation. If you just click that link, I cannot click now since in the presentation mode, but in the normal mode, you can click that and you can go to the paper and read more about it. So due to want of time, I'm just skipping this. The second application is this one. What is this? So it's nothing but connected and autonomous vehicles. Okay, CAVs. So you can see. No, can you come out? Okay. So anyway, even I have given the reference at the bottom. You can have a look at it later. And then, of course, this is quite interesting, quantum warfare. So it's taken from one journal. You can see the reference at the bottom. You can, yeah, that's a van at the previous one. Good. Ravindra Reddy has mentioned vehicular networks. Yeah, that's what I call connected and autonomous vehicles. Okay. And coming to this, it's a quantum computer connecting quantum underground mappings, blah, 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 quantum underwater mappings, etc. So maybe due to want of time, I'm skipping this diagram also. But if you want more information and if you're really interested about this research, you can read, you can see the source at the bottom. Can you see that? I mentioned that link. Okay. So you can use that and you can have a look at it. Now, what the industry thinks about. So as I told you, maybe I'll talk about three things. One is IBM, another one is Google, and then the last one is from Intel. Okay, so the first one is IBM. So they are leading in this quantum computing arena. Watch this video. You can see that at the bottom they have mentioned IBM quantum system 24x supports 1000 plus physical qubits, 15,000 plus quantum gates are there. So this is how the actual IBM quantum computer looks. So it's called as Blue J. You can see the name at the left-hand side bottom. It has got 2000 logical qubits, 1 billion quantum gates. Okay. Yeah, Ravindra, you are absolutely correct. Looking like a first generation classical computer, room sized, right? Yeah, that's correct. Okay, so this is the overview of it. So they call this as the bicycle architecture, and the main criteria for this IBM is that scalable quantum computing. They concentrate on certain things like actually they have introduced one processor. Can someone tell me the name of the processor introduced by IBM in 2025? Someone can ask Google and tell. Okay, no problem. I'll just tell. It's called as Kookaburra. Kookaburra. Okay. I'll repeat again. Kookaburra. Kookaburra. So this is the processor unveiled by IBM in this year, 2025. So it is a 1386 qubit multi-chip system. Okay. So it has got something like 4,000 qubits embedded in it. So the main aim, as I told you, is like scalable computing. Okay. And then IBM also has got another thing called as Loon processor, LOON. There's another processor. I think, yeah, I have mentioned it over here. So you can see it also works with Boeing, Cleveland Clinic, Oak Ridge National Laboratories, etc. And they are also focusing on the things like fault tolerant systems, addressable, universal, adaptive, modular, efficient quantum computing. So this is the goal of IBM. IBM has also got its own software tool which is called as Qiskit, Qiskit, pronounced as Qiskit. I repeat again, it's Qiskit. Qiskit, it's a serverless tool. It allows for execution of the quantum workloads across the quantum and classical systems across, right? It's a transpiler. I think I told about what is transpiler earlier. It's a transpiler based system. Okay. So next is this is the roadmap of IBM 2025. Okay, you can have a detailed look at this later. I'll just move on to the next slide. Next is from our most used till now, right? Most of us were using Google. So what about Google? So they have their own quantum AI. Please watch this video.
Hi, I'm Julian Kelly, Director of Hardware at Google Quantum AI. Today, with an amazing team, I'm proud to announce the most powerful superconducting quantum computation. Step in our path towards building large-scale computers and exploring their applications. I've been fascinated with quantum computing since I first experimented with Qubits in 2008. And since coming to Google in 2015, it has been a dream to make our mission. Quantum computers for otherwise unsolvable problems. We launched our first chip Foxtrot in 2017, followed by Prasanna in 2018, and Singapore in 2019, which covered step 1, the first quantum computer to surpass the best classical supercomputer computational task, random circuit sampling. Over the years, Singapore, we have been space the scale of quantum computing ultimately been limited by quantum coherence times, the length of time qubits maintain their intended state. as well, we made a huge step forward. So times by a factor of 25 seconds in second more to 100 microseconds in 1 minute.
Okay, they concentrate on coherence. We all know that IBM was concentrating on scalability. So they have their own roadmap for what they are going to do in 2025. Okay, this is about Google. And next is like Intel. You know, whenever we talk about classical computers, Intel comes into our mind. Am I right? Processor means Intel, right? Till now. i3, i4, sorry, i5, i7. We started with Intel 8086, 8085. Okay. So what about Intel? What they do in quantum? So you can see the quantum computer here. James Clark was the scientist who worked on it. So they are developing a 12-qubit chip. So you can see him holding that device, the small thing. Okay. So this Intel Quantum, actually they use a spin qubits. I think we spoke about what is a spin qubit, and they have control, and this is the architecture. You can see how it actually works. So the full stack of this quantum architecture, we have at the bottom the qubit hardware. We have spin qubit, Intel Quantum Simulator, control electronics, qubit control processor, runtime compiler, and the application. So we work on the applications part over here, and the rest or here. This is the full stack of the quantum full stack approach. So since I think it's 7:26 and I have another 4 more minutes, the session is open for some questions now.
So you said that other type of quantum computers are quite slow as compared to superconducting.
Compared to?
Superconducting quantum computers.
Yeah, you can see that all the 3, whatever I showed, they use a superconductors, right? Even you can see, okay, they use the word supercompute, scalable quantum, okay. I think in the video they were talking about that. So superconductors are used since data transfer is to be so fast. And in a normal conductor, we know that resistance will be there, and resistance will take the data transfer a much more timer. By that time, the state of the qubit may change. Okay, so it has to be done instantly without any delay, any further delay. So they go for superconductors. Even you can see like there are a million times smaller than a smaller superconducting qubit. Yeah, thank you, Ravindra Reddy, sir. Thank you so much.
Thank you, sir.
Okay, so maybe in the presentation at the last, I've given my contact if anyone is interested to work or do some research on quantum machine learning. Basically, you know, I'm working in this yellow color thing, application algorithms. Okay, so I work on bioinformatics related to quantum computing. So if anyone interested, you can either WhatsApp me or you can contact me through my official mail ID, which is displayed over here, or you can just contact me through LinkedIn. So I think I have to thank all the organizers. It was a seamless coordination from your side. Thank you so much. Particularly, I thank Chandrakant sir, who was coordinating with me for the past 2 days. Thank you so much.
Sir, thank you, sir. Thank you for your valuable session and spending your valuable time for our ATAL-sponsored faculty development program on quantum cryptography enabled autonomous underwater vehicles. Your presence is more precious for us, sir. We are having one more session to you on dated on 11th, sir. Excellent session.
Yeah, last one.
Excellent session, sir. We are receiving excellent feedback regarding this session, sir.
Thank you, Tam. Thank you, sir.
Thank you for spending your valuable time, valuable and precious time with us, sir. Thank you, sir. Ritika.
So one was asking for the previous slide. Which slide? Ashish, I think he was asking. Which slide? Yes. This one?
Sir, Ashish, sir.
No, no. In the chat, I think 1 minute. Yeah. Ravindra Reddy, can you please display the previous slide? Which one, sir? Which slide?
Thank you, Vishnu sir. Thank you, sir.
Thank you, sir. Thank you.
Ritika?
Yes, sir.
Yeah. Kindly, ma'am.
Dr. R. Prasanna Kumar, sir, thank you so much for delivering an insightful session on quantum hardware, qubits, and superconductors overview. Your expertise and explanations have provided us with a deeper understanding on the fundamentals and applications of the quantum hardware, sir. We appreciate the time you have taken to share your knowledge with us as a part of the ATAL Online Faculty Development Program. Thank you once again, sir, for your valuable contribution to our learning experience. We look forward to apply the insights gained in our future endeavors too, sir. Thank you so much for your presence once again, sir.
Yeah, thank you. Thank you.
Thank you, sir. Prasanna Kumar, sir. Thank you, sir. Thank you very much, sir.
Yeah.
Thank you very much, sir. Thank you, sir.
Thank you very much, sir. It is an excellent session.
Yeah, thank you. Thank you, sir.
Dear participants, Kamala Sethi sir from IIIT-SriCity already will be joined. Take a break for 5 to 10 minutes. Sir is ready to start the session. The next session is going to start 7:30 to 9 o'clock. Take a break for 10 minutes. Already Sethi sir will be joined, who is working in IIIT-SriCity, Department of Computer Science and Engineering. Take a break for 5 to 10 minutes, and dear participants, kindly rejoin the session. requested participants kindly join the session. Already Dr. Kamala Sethi sir has been joined the session. Please kindly join the session. Sir Kamala sir.
I am.
Yes sir. Yes sir. Yes sir. Yes sir. Yes sir. Very good evening sir. Very good evening sir.
Good evening, sir.
Very good evening sir. We are very much grateful. You are going to contribute your valuable deliverables on our ATAL sponsored 1 week faculty development program on quantum cryptography enabled autonomous underwater vehicles, sir. Thank you, sir. Thank you for spending your valuable time for our FDP session, sir. Ma Ritika?
Yes, sir.
Yes, kindly introduce the Dr. Dr. Kamala Sethi, sir, who is from IIIT-SriCity, Department of Computer Science and Engineering. Kindly proceed, ma.
Respected guests, faculty members, and dear participants, it is my pleasure to introduce our esteemed resource person for today's session, Dr. Kamala Sethi, sir. Dr. Sethi, sir, is a distinguished faculty member in the Department of Computer Science and Engineering at the Indian Institute of Information Technology, SriCity, Chittoor, Andhra Pradesh. Dr. Sethi, sir, has completed his PhD in Computer Science and Engineering from the Indian Institute of Technology, Bhubaneswar, and holds MTech in Information Security from National Institute of Technology, Warangal, and BTech in Computer Science and Engineering from National Institute of Science and Technology, Berhampur. Sir is a gate qualified individual having qualified the exam multiple times in the years 2011, 12, 14, 15, 18, and 21. Dr. Sethi sir's research interests include advanced cryptography, attribute-based encryption, homomorphic encryption, machine learning-based malware detection, AI-driven intrusion detection systems, cloud security, and network security. Sir has also published several papers in top-tier Q1 journals, including IEEE Explore, Springer, and other reputable platforms. We are very honored to have Dr. Sethi sir with us today. Thank you so much for your presence with us, sir.
So, thank you for the nice introduction. So, can I share my screen now?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yes, sir. Sir, please permit me 1 minute of time, sir.
Yes.
We are going to introduce Nobel laureates from the year of 2025, sir.
Yes.
Yes.
సార్ మ్యూట్ లో ఉంది సార్.
So good evening, everyone. My name is Sethi. So in this session, before going to next session, we are displaying the Nobel laureates for the physics in 2025. John Clark, Michael H. Dvorak, John M. Martinis. So their discovery started around 1985 to 1986. As well as in previous session, Dr. Prasanna sir have clearly mentioned regarding superconducting qubits. It is the basic foundation laid by these three gentlemen during 1985. So in order to learn about any topological semiconductor, superconductors or trapped ion superconductors, so their the principles are very much needed in order to advance into quantum cryptography or quantum security or quantum communication standpoint. So their discovery is throughout Josephson junction. So if you consider a Cooper page, so electrons and photons exchange through a barrier that is called quantum tunneling. The tunneling mechanism can be understood through a ping pong ball, where if you hit the ball and it bounces back. But in quantum mechanics, if you observe through optical microscope, it goes through other side of the barrier. That is called quantum tunneling. So these three gentlemen have devised a method called photonic integrated circuit using cryogenic hardware. So that is around 10 millikelvin. So Dr. Prasanna sir have mentioned that semiconductor qubits are around 15 millikelvin. But these gentlemen around 1985, they have formulated a mathematical rule that is called topological fermionic state semiconductors. So it is a broad area, but in order to devise and formulate into a mathematical standpoint, so this is one of the area where the research is happening. So it integrates two disciplines. One is regarding semiconductor physics, other is quantum computing and security standpoint. So that's all. We are happy to share the Nobel Prize in physics. This is announced during 4:30 at the evening. So we are happy to share in FDP program. Thank you.
Thank you, sir, giving your valuable time. Kamala Sethi, sir.
Yes, sir. Yes,
Sir, please continue your session, sir. Up to now, he is a IIIT-SriCity student who is pursuing MS in research. Mr. Kanth. Thank you, sir.
Okay.
Thank you.
Okay, sir. My screen is visible to all of you.
Yes, sir.
Yes, sir. It's visible, sir.
It is visible, sir.
Okay. So,
Yes, sir. It is clearly visible, sir.
okay. So good morning, good evening, everybody. So today session is about deep sea security. So integrating traditional, advanced, and quantum cryptography in autonomous underwater vehicles. So this is the basic means outlines of the presentation. First, we will discuss what is autonomous underwater vehicles, then why security is needed, then what kinds of security solutions are there, like symmetric, asymmetric, and what are the limitations of the traditional crypto system, then why quantum cryptography. So first we'll discuss what is AOV. So what is autonomous underwater vehicle? So a autonomous underwater vehicle is a underwater robot that can travel inside the waters autonomously, meaning that it will not require the real-time control from the operators or ships. So that means this autonomous underwater vehicle, they do not require any kinds of control from the users, humans. So before deploying any AOV, autonomous underwater vehicles, so scientists or engineers, first they will program the AOV with the mission plan. So what is the mission plan? It means where the AOV will go and what depth it will reach and what data it will collect. So after the missions, the AOV will return to the surface. Then it will transmit the collected data, and also it can store it for late retrieval. So this AUV means autonomous underwater vehicle. It equipped with sensors, cameras, and navigation system that allows it to carry out different deep sea tasks like mapping, monitoring, and inspection. Unlike UAV, unmanned aerial vehicle, so that moves in air. So AUV, autonomous underwater vehicles, move underwater where GPS and direct radio signals are not available. That means inside the water, so we cannot, the direct radio signals cannot reach there, so we can use the autonomous underwater vehicles. So this UAV can communicate via radio waves, while AUV rely on the acoustics, optimal or satellite-based methods when they surface. So the satellite-based methods they require when they surface. Like since GPS radio signal waves will not penetrate the deep sea waters. So the applications of AUV ranges from the oceanography to defense and resource explorations. So the applications of AUV, next slide we'll discuss. So it is used in different applications like ocean explorations, mapping, environmental monitoring, defense surveillance, and underwater mine detection and naval uses. So first we'll discuss how it is useful in ocean explorations and mapping. So AUV can reach extreme depth where humans cannot rise, humans cannot go. So that's why it provides the valuable information about the geographical data as well as the biological data, like what kinds of marine habitats are there, species distribution, all these things it will give. So also environmental monitoring. So as we know that AUV is equipped with sensors, cameras, and navigation system. So it helps us to measure the different parameters like temperature, pH, oxygen levels, pollution levels. So by the way, we can monitor the ocean health, whether it is in good health or bad health. Also, this AUV can used in defense and surveillance systems. So because AUV can patrol areas quietly and detect the unauthorized submarines and vessels. Vessels are nothing but the large ships or large boats. So underwater mine detection naval uses, AUV also helps the Navy by finding the underwater mines. So that underwater mines that harms ships and submarines. So these mines can harm the ships and submarines. Also, it supports the underwater missions. So in summary, you can tell that AUV is a versatile tool for the scientific research, environmental protection, national security, industrial application in the oceans. The communications in AUV, so there are basically the AUV, the primary communication, they uses acoustic signals because you know that the radio signals cannot travel, especially in the deep sea, like is inside the waters properly. So the traditional wireless methods, like we are using Wi-Fi and cellulars, they are ineffective. So this acoustic signals is the one of the main options that AUV can use. So, but the main problem of this acoustic signal that it suffers low bandwidth, high latency, noise, interference, also multiple effects. So other methods like optical laser links we are using for short range, high speed communications. Also, when the AUV surfaced, it will reach the ground, so it can use the satellite-based communication to transfer large amount of data. So next one, enable data exchange with other AUV, surface vessels and base stations. So multiple AUV, they can work together in a coordinated missions. That means they can map a large area faster. So if you utilize the multiple AUV, they can map a large area faster. So they can transmit the collected data like environmental readings, inspection result to the surface ships. When they surface, the AUV can transfer the large data set via satellite links or Wi-Fi or conventional method like cable docking. So key challenges in AUV, the ensuring the secure and reliable communication in underwater environment is a challenging task because we are using the acoustic signals. But main problem with acoustic signal is it is low bandwidth and also it supports high latency. And encryptions, we are using encryption to protect the sensitive data from the eavesdropping. authentication we are using to ensure that only authorized AOB and vessels or base stations exchange the informations. So error connection techniques we are also using to recover the data lost due to noise. If some data is lost due to noise or desertion, then we can use the error correction techniques. So reliability measures used to overcome the latency, low bandwidth, and signal annihilation. So because of this problem, so AOB faces different challenges. So what are the different threats in the underwater communication? Why the what is the importance of the cryptography? So there are different threats in the underwater communication, like eavesdropping. So acoustic signals can be intercepted by the adversaries. So this is in signal jamming. Signal jamming, this means so disruption and blocking of the communication by sending the large amount of signals. So we can block the communication channel. So that is signal jamming. And data tampering. Data tampering means unauthorized modification of the transmit. If some data is transmitted by AOB, if the data will be unauthorized modified by some attacker, so this is nothing but the data tampering. And unauthorized access and control means so gaining control over the AOB without permission. Somebody gains the control over the AOB without the permission from the owner. That is unauthorized access and control. So importance of the cryptography for the AOB. So that means it helps for the data protections, like it ensures the confidentiality, integrity, authenticity of the informations. Also, the cryptography helps in access control. That means prevents unauthorized manipulations on control of the AOB. Also, this cryptography helps to strengthen the reliability in multi-AOB networks and mission-critical operations. So cryptography, so there are different cryptography solutions we are using for the underwater communications, like symmetric cryptography. For in AOB we are using the symmetric cryptography provides the fast communications, but main problem is that so making it ideal for the low bandwidth and underwater communication. This is the advantage of the symmetric cryptography. It provides the fast encryption. So in asymmetric cryptography, asymmetric cryptography means we are using the public key cryptography for the secure key exchange. So basically, the elliptic core cryptography is preferred in public key cryptography due to the smaller key sizes and higher efficiency. So also the advanced cryptography like attribute-based crypto systems and homomorphic crypto system is used on UV communications. So attribute-based communications allows fine-grained access control. So means only AOB autonomous underwater vehicles with correct attributes can decrypt the sensitive mission-critical data. In homomorphic encryptions means it enables the computation on the encrypted data without the need of the decryptions. That means it supports the collaborative processing among AOB swans. Means because the AOB data contains some critical information, so that without decrypting, if you are performing the computation directly on the cybertext, that is the homomorphic encryptions. Now, what is the problems with the traditional cryptography? So traditional cryptography supports the limited bandwidth in underwater communications. A limited bandwidth in underwater because we are using the acoustic signal, which is limited bandwidth. So this makes the encryption overhead problematic. So another one is high latency. The high latency in acoustic signals reduces the efficiency of the key exchange. That means it is vulnerable to different kinds of attacks, like because of the high latency. So it is vulnerable to interception, replay attack, main in the middle attack. Also, the traditional key distribution like RSA we are using and elliptic or cryptography that requires a computational resources. They require computational resources that drain the AOB's limited energy supply because AOB's has limited energy. So if you are using the traditional key distribution methods like RSA-CC, it will drain the computational resources. So difficulty in securely updating the key during the mission in remote and holistic environments. So also this is one of the problems in the traditional cryptography in AOB environments. So how it can be mitigated using the quantum cryptography? So quantum cryptography means quantum key distributions ensures the unbreakable encryption key by leveraging the quantum states. Means we are using the quantum physics by the laws. We are using the laws of the quantum physics. So the keys are exchanged using the photons. Photons means ensuring the detection. If means the state of the photon is changed, easily it can be detected if someone is means compromising our communications. So it is also suitable for highly secure AOB missions. That means this kinds of like naval defense and sensitive explorations. Also, it reduces the computational load since security relies on the physics, not the Platts prime factorizations. If you are using the traditional cryptography, the security depends on the computational problem, like the complexity of the NP hard problems. But here the security depends on the in quantum cryptography, the laws of quantum physics. So enables the secure communication links between AOB fleets and command centers in critical missions. So this using the quantum cryptography, we can enable the secure communications between the AOB and command centers. So now we will discuss briefly because we will discuss the cryptography concepts. Then we will discuss the symmetric, then public crypto system. Then we will discuss the advanced crypto system. Then we will discuss the quantum cryptography and how it is useful in the AOB communications. The cryptography, I think all of you know that what is cryptography. Cryptography is a science of secret and hidden writings. So the job of the cryptographer is to design a coded message so that nobody can understand. But the crypt analyst's job is different. So their job is to obtain the meaning of the encoded information or encrypted information without accessing the secret information without the requirement of the key. If they try to understand the meaning of the message, that is nothing but the crypt analysis. The cryptography is a combination of the cryptology is a combination of the cryptography and crypt analysis. So the different terms we are using the cryptography like plain text. Plain text is nothing but the original message. And the ciphertext is nothing but the coded message. And the algorithm that we are using for converting the plain text to the ciphertext, that is the encryption algorithms, which is done by the Alice in this case. Alice converts the original message to the coded message by using the encryption algorithms. The decryption is nothing but the recovering the plain text from the ciphertext. That means the decryption algorithms will take the input from the input like ciphertext and it gives us the plain text. The key is the secret information that we are using the for encryption and decryption. So encryption we are using the encryption key. For decryption we are using the decryption key. Does this secret information like the key is known to only sender and receiver. So it should not be disclosed to any unauthorized party. What are the main goals of the cryptography? The main goals of the cryptography is like confidentiality, integrity, authentication, non-repudiation. What is the confidentiality means? Suppose Alice and Bob, they are two parties, they wanted to communicate to each other. The main requirement is that when Alice is sending some information to Bob, except Alice and Bob, nobody can understand the meaning of the message. That is nothing but the confidentiality. That means only authorized parties should understand the meaning of the message. Unauthorized parties like he cannot understand the meaning of the message. Integrity means when Alice is sending some information to Bob, the main requirement is that whatever the information Alice sends, same information should be received by the Bobs. Except Alice and Bob, nobody can change the modify the informations. So that is means integrity means only unauthorized entities can modify the message. Only Alice and Bob can modify the information. Except Alice and Bob, nobody can modify the message. So authentication means sender receiver need to confirm each other's identity. When Alice is sending some information to Bob, Bob need to identify that I am communicating with Alice. Alice needs to identify that I am communicating Bob. That is authentication. So non-repudiation means assurance that someone cannot deny something. When Bob receives the message from the Alice, Bob cannot deny that I have not received the message from the Alice. So that is the non-repudiation. And thus, there are two kinds of cryptography. One is symmetric cryptography, one is asymmetric cryptography. In symmetric cryptography, we are using the same key for the encryption and decryptions. So if you means for encryption, whatever the key we are using, for the decryption, same key we are using. All the traditional schemes, crypto systems are symmetric crypto system like shift ciphers. In shift ciphers, that means suppose a message is here, you can shift to 2 bits. The encryption is equal to like, if you shift 2 bits, it should be C. So if you are shifting the 3 bits, then 3 places, then encryption of page should be D, like that. This is the shift cipher. So symmetric key cryptography also divided into 2 types. One is block ciphers, another one is stream ciphers. So what the block ciphers will do, block cipher encrypt 1 block at a times. So typically the block size is called 64 bits or 128 bits. The examples is like AES-DS, Advanced Encryption Standard, Data Encryption Standard. They are using the block ciphers. That means we can encrypt a block at a time. So instead of AES, the block size is 64 bits. Instead of AES, the block size is equal to 128 bits. Instead of DS, Data Encryption Standard, the block size is equal to 64 bits. In stream ciphers, we can encrypt 1 bit or 1 byte at a time. One example of stream cipher is RC4 algorithm. The symmetric cryptography, the strength of the algorithms, like symmetric algorithms, is determined by the size of the key we are using. So that means longer the size of the key, more difficult to crack the symmetric ciphers. So the key length in symmetric key crypto system is expressed in bits. So typically key sizes vary from 48 bits to 448 bits. The set of possible keys for a cipher is known as key space. Like for suppose we have a 2-bit key. That means what are the possible keys are there? 2-bit key means the key possible keys are like 00, 01, 10, 11. So like these are the key space. Suppose if it is a 3-bit key, the set of possible keys may be 000, 001, 010, 011, 100, 101, 110, 111. So like this. That means these are the key space. So to crack the key, the attacker or hacker is to use the brute force attack. So what is the brute force attack means? In brute force attack, the attacker try all the possible key combinations, still the key that works is found. That means suppose we are using the 2-bit key. So in 2-bit key, what are the different possible key combinations like 00, 01, 10, 11. Out of these 4 possible keys, we are using 1. So what the attacker will try all possible key combinations. Still the key that was is found. So this, if you use the supercomputers, they can crack a 56-bit key in 24 hours. So that we can use key size more than the 56 bits. So if you are using the 128-bit key, so it will take 2 to the power 72 times. That means longer than the age of the universe to crack the key using the brute force attack. So limitations of the symmetric key cryptography. So any exposure to the symmetric key compromises the secrecy of the ciphertext. That means a same key we are using for the encryption and decryptions. If attacker get access to the key, so it will compromise the security, it will decrypt the ciphertext and see the actual plaintext. That means any exposure to the secret key compromises the secrecy of the ciphertext. So a key needs to be distributed to the receiver for the decryptions. So that means, so because we are using the same key for encryption decryptions, so if sender encrypt the message using a key, the same key need to be transmitted to the receiver, because you know that when you are transmitting the key to the receiver, so we are transmitting the key over an insecure channel. So that means, so there is a chances of compromising the symmetric key. So there are the different limitations of the symmetric key. So now we will discuss another cryptography like asymmetric cryptography. As you discuss in symmetric cryptography, symmetric means same key we are using for the encryption and decryption. But in asymmetric cryptography, we are using the different keys for the encryption, different keys for the decryptions. So in asymmetric key cryptography, we are using two kinds of keys. One is public key and the other one is private key. So public key we are using for the encryption purpose and private key we are using for the decryption purpose. So for message encryptions, we are using the public key and private key is used for the decryptions. Suppose now there are two parties, Alice and Bob. So Alice wants to communicate some information to Bob. So if we are using the asymmetric cryptography, then when Alice wants to send some information to Bob, then Alice uses Bob's public key. That means, so then to encrypt the message, Alice uses the Bob's public key. So whenever the message is encrypted message received by the Bob, so it can decrypt by using his private key. But also in asymmetric cryptography, so main problem is that we are using the public key for the encryptions. Because public key is used, why it is public key? Public key is known to everybody. So what is the main security that, so nobody can retrieve, because public key is known to everybody, nobody can retrieve the private key from your public key. So that is one of the main requirement in the asymmetric cryptography. The limitations of the asymmetric cryptography lies, encryption is slower than symmetric cryptography due to use of longer key length and complexity of the encryption algorithm. So in asymmetric cryptography, we are using more complex algorithms. Because of that, the encryption is slower in comparison to the symmetric key cryptography. The key validations also, as public key is known to everybody, we need to validate. So because Alice's public key is known to everybody. If somebody receives Alice's public key, then we need to sure that whatever the public key we are using, that is Alice's public key, not anyone's public key. So somebody should be there to certify that this is the Alice's public key, not Bob's public key. So that is the concept we are using, a digital certificate one concept that is using, that is out of the scope of the talk. So that is a digital certificate we are also using to validate. So the limitations of the traditional crypto system. So as we discussed, the traditional crypto systems like this symmetric cryptography, asymmetric cryptography, like means asymmetric cryptography in public cryptography, symmetric means this is a private cryptography. So we can achieve the confidentiality by using the symmetric cryptography, also asymmetric cryptography. But what are the main limitations? The main limitations is that it lacks the data scalability. Data scalability, so this will not work if we have huge amount of data, we wanted to encrypt the data. That means it lacks the data scalability. So that is the thing. So another one, it will deploy the public PKI, means public infrastructure certificate management functions. Also, it do not allow the computations on the ciphertext. If somebody wanted to perform some computation on the ciphertext, it will not allow to perform computation directly on the ciphertext. So it lacks the expressiveness of the data sharing also. That means if somebody wanted to share the data to multiple users, so in that case, if you are using the traditional crypto system, that is not suitable. So also one of the another question, that is the main thing, that it do not allow computation on the ciphertext. Means if you are using to perform some computation on the ciphertext, this should not be supported by the traditional crypto system. So first, the traditional crypto systems takes the data to the user end, then it will decrypt it. Then after decrypting, then we can perform some computation on the data. But so this is the one of the, because the overhead, there is a lot of overhead is there. So the traditional crypto system, if you see that, so you see that the traditional crypto system is secure but inefficient. So what is the inefficient means? Suppose you have one piece of data, you wanted to share the data to multiple users, the same data. So what you have to share the data to multiple users, you have to create different encrypted copies of the same data by using different keys. That means same data, but what we are creating different encrypted copies of the data to share to the different users. So that is one of the major limitations of the traditional crypto system. Too many encrypted copies of the same file, because we in the computer we have limited space, because if you create the same encrypted copies, many encrypted copies of the same file, it will unnecessarily waste our memory. So advanced crypto system, to overcome the limitation of the traditional crypto system, so we are using the advanced encryption techniques. So there are two advanced encryption techniques. One is attribute-based encryptions, another one is homomorphic encryptions. So attribute-based encryptions provide confidentiality and fine-grained access control of the data. So here the means we are encrypting the data for a group of users. So if you are using the traditional crypto system, it provides one-to-one mapping. That means so data we are encrypting for a particular user, but using attribute-based encryption, we are encrypting data for a group of users. So there are two kinds of attribute-based crypto system. One is KPAB, one is CPAB. Key policy attribute-based encryptions, KPAB, and CPAB means ciphertext policy attribute-based encryptions. So another kinds of advanced crypto system is like homomorphic crypto system. So homomorphic encryption allows computation directly on the ciphertext. Like in the traditional crypto system, they do not support directly computation on the ciphertext. So it eliminates the decryption of the ciphertext. So because in the traditional crypto system, if somebody wants to perform a computation, you need to decrypt it. So there are three kinds of homomorphic crypto systems are there. One is PHE, partially homomorphic encryptions. SHE means somewhat homomorphic encryptions, and FHE means fully homomorphic encryptions. So this is the fully homomorphic encryptions. Okay. So next one is the traditional crypto systems don't. So the main motivation we will discuss why homomorphic encryption. As you know that the traditional crypto systems do not allow computations directly on the ciphertext. If somebody wanted to perform some computation on the ciphertext, then first we need to decrypt the ciphertext. Then after that we can perform the computation. But in case of homomorphic encryptions, so it can directly perform computation on the ciphertext. So that means it by the way we are eliminating the decryption of the ciphertext. So what is homomorphic encryptions? As I discussed, we can perform computation over the ciphertext without the decryptions. So that means we can outsource the calculation on the confidential data to the remote server. So there are basically four functions are there. If any normal encryption algorithms, we have three functions. So one is like keep keys and encryptions, another one is decryptions. So but in homomorphic encryptions, so in homomorphic encryption there is extra function like evaluation functions. So evaluation function actually performs computation directly on the ciphertext. So the homomorphic encryption satisfies two properties. One is additive property and then one is multiplicative property. The additive property means encryption of M plus M1 is equal to independent encryption of M1 plus independent encryption of M2. That is the additive property. So next one is multiplicative property. Multiplicative property means encryption of M1 and M2. Encryption of multiplication of M1 and M2 is equal to encryption of M1 multiplied by encryption of M2. So that is the multiplicative property. So this is the workflow of a homomorphic encryptions. So first, the client encrypts the message M and sends the message, encrypted message to the remote server. This is the remote server is sending the message. Then after that, the remote server performs suppose this client wants to perform some addition operations on the message. So it will send the encrypted message to the remote server. The remote server performs computation directly on the ciphertext. It will perform the additions and also it will return the encrypted result to the Bob. Encrypted result to the client. Then after that, the client will decrypt it to get the original result. So it will decrypt it to get the original result. This is the workflow of a homomorphic encryptions. The as we discussed, there are three kinds of homomorphic encryption. One is partially homomorphic encryption, and the other one is fully homomorphic, and the other one is somewhat homomorphic encryptions. The partially homomorphic encryption supports either additive property or multiplicative property. So that means it supports either addition or multiplication on the ciphertext. So some example like RSA crypto system, Elgamal crypto system. So these crypto systems are satisfying multiplicative property. So these are only, but they do not support the addition property. So this is a partially homomorphic encryptions. So if bilinear encryptions, it satisfies the addition of the ciphertext, but it does not satisfy the multiplication of the ciphertext. So this is the things. So that means these are called the partially homomorphic encryptions. But main limitation of the partial homomorphic encryption, as you know, that it is supports either addition or multiplication of the ciphertext, but it cannot support both properties together. So that's why we are using a fully homomorphic encryption. It supports two properties together. One is addition, another one is multiplication with unlimited number of times on the ciphertext. So this fully homomorphic encryption satisfies both properties like additive property and multiplicative property. So Gentry is a scientist. In 2009, he proposed an idea to construct the fully homomorphic encryption from somewhat homomorphic encryption. The somewhat homomorphic encryption differs from the fully homomorphic encryption in what way that? So in fully homomorphic encryption, we can perform unlimited number of computations like addition, multiplication operation on the ciphertext. But in somewhat homomorphic encryption, it can perform both addition and multiplication on the ciphertext, but with limited number of times. So that is with limited number of times. But in fully homomorphic encryption, it can satisfy both operations like addition and multiplication with unlimited number of times. So Gentry, so as I told you, Gentry given the idea to construct the fully homomorphic encryption from somewhat homomorphic encryptions. So it uses because when we are performing computation on the ciphertext, it will add lot of noise in the ciphertext. If somebody wanted to decrypt the ciphertext, it will not get the actual results. So that's why we need to replace the ciphertext so that the replaced ciphertext is less noise in comparison to the original ciphertext. So that's why the Gentry uses a procedure called bootstrapping procedure to replace the ciphertext. So the replaced ciphertext has less noise in comparison to the original ciphertext. So this is the bootstrapping. This operation on the ciphertext adds the noise. The decryption is not possible if the noise reaches a threshold value. So even if we decrypt, so we will not get the actual result. So that's why we need the ciphertext replace procedure. So this is the ciphertext replace procedure we are calling it the bootstrapping process. But the ciphertext replace procedure is very computationally expensive. So it is not suitable for the practical application. So one of the homomorphic encryption that we will discuss, that is DGSB homomorphic encryptions. So this is a DGSB homomorphic encryptions. So it uses a shared. Yes.
So what is DGHB?
So DGSB is a four scientists. Means there are the name of the scientist means DGHB. There are four scientists based on their names. We constructed them.
Sir, can you please elaborate it, sir?
So we are next slide. We are elaborating the DGSB encryptions. Okay. So DGSB encryptions. So how it is happening? So this is it uses a prime number P. So this is a secret key. So suppose we wanted to encrypt a n-bit message. M1, M2, there are n-bit. M1 either 01, M2 is 01, M2 is a n-bit message. So this DGSB encryption is a performs bit level encryptions. Bit level encryption means we have to encrypt each bit independently. So like this, if you see that, so if it is a n-bit message, we are performing n encryptions. Like we have to first encrypt the first bit, then we have to encrypt the second bit, then we have to encrypt the third bit. Like that, we have to encrypt the nth bit. So like this, we can also get the all the ciphertext like C1, C2, Cn. So again, what is the logic we are using to encrypt a bit? So to encrypt a bit, we have to choose a random number like Q. Also, we use a small r, like r is a noise. So that means the output should be this is the C that we are using, PQ, P into Q, that is P is the prime numbers, Q is the large numbers, and 2R plus M. This is the 2R M, that is the noise component. If you do this 2R, so that's why the bootstrapping process is required, because this 2, for the correct decryption, the 2R plus M should be smaller than P. If the 2R from M should be larger than the P, then the decryption is not possible. That's why we need the ciphertext refresh procedure. To decrypt the C, we can perform C mod P mod 2. Okay. So this is the thing. You see in this example, so like there are two like ciphertext, one is C1, another one is C2. So that is also we are using the Designation encryption, like, and so we wanted to perform the addition of the ciphertext like C1 plus C2. So if you see the C1 and C2, so what problems are Q1, like Q1 plus Q2P? So we are mapping, we are converting in the form of Designation encryptions. So if you see in this example, the noise component is there. So what is the noise component? 2 into R1 plus R. If this component is less than P, then we can easily decrypt the ciphertext. Now, if you perform the multiplication, if you see in this example, so if you see the noise because now if you notice the multiplication, if somebody notice the addition, where the noise is more, can anybody tell? That means in the multiplication process, the noise component is more in comparison to the additions. Is it fine? So now, so if this noise reaches a certain threshold, then even if we decrypt the ciphertext, we will not get the actual result. That's why we need so this noise grows after each operations. So after some operation, the ciphertext becomes undecryptable. When this component is more than P value. So this DGH encryptions can perform a lot of additions, but it can perform a limited multiplication, because if you see that additions, because noise component is less in case of additions, but the noise is more in case of multiplications. That is so this noise must be less than P for the correct decryptions. So therefore, we can call the DGH encryption scheme is a somewhat homomorphic encryption scheme. Okay. So that's why the Gentry proposes the idea that converted the somewhat homomorphic encryption to fully homomorphic encryption by using a procedure called bootstrapping procedure. So what the bootstrapping procedure will do, the bootstrapping, after each operations, the noise is added. So when the noise will reach a certain threshold, we cannot decrypt even if we decrypt the ciphertext, we will not get the correct result. So that's why using bootstrapping process, we can reduce the noise in the ciphertext so that we will get a refreshed ciphertext. So we can, even if we decrypt the refreshed ciphertext, we will get the correct result. So that is the all about the homomorphic encryptions. So next we will discuss another. So what is the advantage of the homomorphic encryption? As I discussed, the homomorphic encryption performs computation directly on the ciphertext. So next one is the traditional, another limitation that of the traditional crypto system. The traditional crypto systems, so what problems will happen? In a traditional crypto system, we are encrypting the data for a particular user. So if somebody wants to share the data to multiple users, so that we have to create the multiple copies of the encrypted data, so that it will unnecessarily waste a lot of memory in the computer. So that's why it lacks the expressiveness of the data sharing. So what we can do, attribute-based encryption, so we can encrypt the data for a group of users instead of a single user. So share the encrypted data for a group of users instead of a single user. So different users access different parts of the encrypted data, thereby it provides the fine-grained access control over the encrypted data. So here user identity is generalized to a set of attributes in case of this AB. So this is the attribute-based crypto system. It is also a type of public key crypto system in which the secret key of the users and the ciphertext are dependent on the attributes. So it is the first proposed by this attribute-based crypto system is proposed by the Amit Sai and Brent Waters in 2005. Then there are two variants of the attribute-based crypto systems are there. One is key policy attribute-based encryption, and another one is ciphertext policy attribute-based encryption. So it is a key policy attribution. Key policy means the policy is attached to the key. So attributes are associated in key policy attribution encryption. The attributes are associated with the ciphertext, and the access policy is attached to the user secret key. So this policy is nothing but using a set of descriptive attributes. We design the policy. You see that the R6 policy is defined as a set of rules on a given set of attributes. The user is able to decrypt the ciphertext if only the access policy that is embedded in the secret key is satisfied by the attributes associated with the ciphertext. So, but what is the main issue with the KPIB? That the data owner has no power to decide who can access the data except using a set of attributes for the data. The data owner cannot decide to whom it will give the access to the data. So only it can choose a set of attributes, except that it does not have any power. So this restricts the possibility of the or usability of the KPAV systems for practical applications. If you see this example, so here's the secret key is associated with some policy. So if the secret key that is associated with if the policy that is associated with the secret key satisfy the attributes of the ciphertext, then the user is able to decrypt the ciphertext. So another variants of the attribute-based encryption is like CPIB, ciphertext policy attribute-based encryptions. So it is a tool that is used for fine-grained access control over the encrypted data. So here the user is defined a set of descriptive attributes. The private key, it depends on the user's attributes and issued to the users by an authority, this private key. That is a reverse. That means here in ciphertext policy means the policy is attached to the ciphertext and attributes are associated to the users. That is the main difference. So this is the associated. So that means here in this example, access policy is attached with the ciphertext and the attributes are associated to the users. If the attributes that is associated to the user satisfy the access policy that is associated to the ciphertext, then the user is able to correctly decrypt the ciphertext. That is the if and only if the attributes of the user satisfy the access policy of the ciphertext, the user can able to decrypt the ciphertext. So this is an example. I will show how the CPAG works. So this is a certified, this is an authority. The authority will manage a attribute universe. So attribute universe means it is a different kinds of attributes like department, CSE or EE, type of student is a PhD students, alumni. It is a gender means it is a male students or female students, birth year, all these things. It will manage different variants of the attributes. So now another party is there. So based on the attribute inverse, so it will generate the two keys. One is master secret key, and the other one is private key. Now public key, master secret key, and another public key. So now this is a data owner. The data owner wants to encrypt the message here and wants to store the encrypted message in the remote server. So now for encryption, the data owner takes 3 arguments. So what are the 3 arguments? One is this is the
Sir, could you please share the screen? Slides are not visible, sir.
Yes, sir. Sir, Ravindra Reddy, sir. Sorry for the interruption, sir. It will be held on the resource person side, sir. Hello, Ravindra, sir.
Yes, sir. So I will connect it,
Yes,
sir.
sir.
That
Yes,
is.
Yeah, thank you,
can
sir.
you please-
Yes, sir. Yes, sir. So, sir will be joined, sir. Kamala Sethi sir will be joined, sir.
Okay, sir. Thank
Please
you.
wait
Thank
1
you.
minute, sir. 1 minute, sir.
Okay.
Sorry,
So
sir.
yes, sir. So there is some problem, internet problem. So in my.
Yeah, no worries, sir. No worries, sir.
Okay.
Okay, sir.
No worries.
Okay.
Yes,
So
sir.
okay. So
Sorry for the interruption, sir.
Okay, thank you, sir. So you see, this is the PPT is visible to all of you. My PPT is visible.
Yes, sir. Yes, sir.
Okay, okay.
Yes,
So
sir.
as
Now
I
it is clearly visible, yes.
okay. So I think so. You see that. So what problems will happen? The user will. You see that this is the policy, as I told you. The for the when we are encrypting the message. When we are encrypting the message, we are attaching the policy with the ciphertext. This policy is attached to the ciphertext, and we are store the encrypted message in the remote server. That is the ciphertext stored in the remote server. Now you see, so there are two users are there. The two users are there. This user has the attribute CS and PhD student. So this is a computer science PhD student. So it will give each attribute to the authority, and authority will verify his attributes and issue a secret key. So now using the secret key, so similarly another student is a PhD student in double E branch. You will issue the secret key to the authority, and authority, certified authority will give him a secret key SKB. So now, can anybody tell out of two users, which user is able to decrypt the ciphertext, which user is not able to decrypt the ciphertext? If you see in this example, it is a CS PhD student, because if you put this policy in the if you put this attribute in the policy, is it true or not? CS means CS student is there and also PhD student is there or GET is there. That means his policy is satisfying. That means this user is able to decrypt the ciphertext because that is attributes like CS and PhD satisfying this policy. So can you tell whether the second user is able to decrypt the ciphertext or not? If you put this double A branch here, because there is no attribute like double A branch and PhD even because this is false and this is also true. That means it is also AND gate means it is false. Okay, so that means this user, second user is not able to decrypt the ciphertext.
No, sir. No, the second user does not able.
Because the policy does not satisfy. Okay, this is the beauty of the attribution. Because why it is used for? Normally in autonomous area vehicle, there are multiple means autonomous area underwater vehicles are there. Every underwater vehicle is different kinds of attributes. So if they wanted to means get access some sensitive information, they can apply these kinds of mechanisms there. Okay. So now what is the security of the CPIB system? If none of the users can decrypt the ciphertext individually, still they cannot even do if they work. So like this, you see, this is a very interesting. If there are two users are there, so this is a user, this is another user, because this user is not able to decrypt the ciphertext because his attribute does not satisfy the policy. So similarly, another user is there. So this user is not able to decrypt the ciphertext because its attributes does not satisfy the policy. So now, what they will do, if they are very intelligent, they will think that we will combine our attributes, we will try to decrypt the ciphertext. Is it possible? Even if they will combine their ciphertext, still they cannot decrypt the ciphertext. You see that. So what they can do, they are combining the ciphertext, SB and ST. Still, is it satisfy the policy? It will not satisfy the policy. So that is now collision resistant. Even the multiple users, they will collude their attributes if they cannot decrypt the ciphertext. Okay. So this is so the limitations of the AB. So like that computational cost during the decryption phase grows with the complexity of the access policy. If the access policy is more complex, the decryption also takes a lot of times because we need to verify all the attributes is there in the policy or not. So that we have to satisfy. So it will take a lot of time. Also, single attribute authority has to issue private keys to all the users. So if because in attribute-based encryption, we are doing encryption for multiple users. Suppose you think a scenario where multiple autonomous area vehicles are there. So they want to means access sensitive informations. So they will issue they wanted to get the private key. So they will request all the information to the authority. So in that case, if authority is very busy persons, so that means he cannot remain online 24/7. So that problem is there. That means the single attribute authority has to issue the private key to all the users. So also revocation of any single private key. If one of the private key is revoked, if any one of the users private key are revoking, then still that user is not able to decrypt the ciphertext even if his attribute satisfy the policy. That is one of the challenging tasks in the attribute-based encryptions. So that's why another concept we are using, the multi-authority CPIP system. So it might not realistic to have the single authority to manage all the attributes of the users. So a data owner wants to share the data with users who are the computer science alumni of University X and currently working as an engineer for company Y. So access policy, if you see, this is the access policy consists of, so that means the same users, but he is previously he was a computer science student of the university. Currently, he is working in the university of the company for Y. So now, if you see in this scenario, the user contains attributes that belongs to same authority or different authorities. That belongs to different. One authority is University X, and other one is company Y. So the access, the access policy also. So different domains of attributes are managed by the different authorities, like the CS and alumni are the attributes that is managed by the University X, and alumni and engineer attributes managed by the company Y. The data owner encrypt the message with the access policy over the entire attribute inverse. So now if you see this example, so if you see that this is a university, the university manages a set of attributes, CS and EE, alumni, PhD. So for all the attributes, it will generate the private key component and public key component. Like CS, it will generate one private key component for EE, for PK, for all these things. So similarly for the company Y, so there are many attributes like engineer, worker, manager, develops. It will generate the two components. One is private key component and another public key components. So now, so this is the users. The users, this is a user. The user wants to access the ciphertext that is encrypted with this policy. So that is CS, manager, and engineers. So these users, if you see that, these users, to decrypt the ciphertext, you will get the secret key because these users, if you see these users, if you see that, these users first will get the private key component from this authority, like the university, because the university managing the computer science students. So also it will receive the managers and developer these components from the company Y. So now, then this is the data is encrypted with this public key components. That means this public key components of the computer science students, also this components. Now, if you see these users, the CS and engineers, so how this user is able to decrypt the ciphertext? So first, to decrypt the ciphertext, this user will receive the private key component from the University X. That is the private key component related to CS, like this is the. Similarly, this user also receive the private key component related to engineer from the company Y. This is the company Y. After that, it will combine the secret key components, and that is the combine the secret key components CS and engineer. And using this component, you wanted to access the ciphertext that is encrypted with this policy. So now, if you see this policy, definitely will satisfy the access policy. These attributes will satisfy the access policy. So this user is able to access the ciphertext. So this is the working of the multi-authority system. That means in multi-authority system, the different authorities will manage different sets of the attributes. So that means the limitation of the multi-authority system, like so it is existing multi-authority system, it lacks the I-expressiveness. I-expressiveness means the access policy is restricted to only the AND gates. But in real-time scenario, the access policy may contain AND gates, OR gate, all these things. So also small inverse system. If this university has 100 attributes, it has to generate the 100 public key components, 100 secret key components. That is the things. That means small inverse means, that is the small inverse means 100 attributes implies the 100 secret key components, 100 public key components. So instead of doing this one, can we generate one public key component and one private key component? So that is possible using the large attribute inverse model. So this is the thing. Also, the traditional multi-authority CPF systems are inefficient because they are using the composite order groups, like these are the different composite, because computation in the composite order groups will take large amount of time. So also the global trusted authority, even if the there are different sets of attributes are managed by the different authorities, still they have to trust as central authority. So that's why. So we are moving to the quantum cryptography concepts. So now we'll discuss what are the limitations of the traditional crypto systems. So the traditional crypto systems, as I discussed, they provide the faster encryptions, so making it ideal for the low bandwidth underwater communications. But what is the main problem in the traditional crypto system? The security of the symmetric crypto system depends on the secrecy of the share key. So that also we need to establish the secret key before the communications. That means if Alice and Bob, they wanted to communicate to each other using the symmetric cryptography, they need to establish the key. If the key is exposed, then definitely security will break. So that means also the key distribution we are using to transfer the secret key from sender to receiver, we are using the public key methods also. Different kinds of methods that we are using, a defilement method, all these methods. So similarly, in the public key cryptography, the security of all the public key cryptography, in public cryptography, as we discussed, we are using two types of key. One is public key for encryption and private key for the decryptions. So the security of the public key cryptography depends on the NP, means mathematical hard math problems. Like if you see the RSA crypto system, the security of RSA crypto system depends on the prime factorization problems. Also, the elliptic curve cryptography, the security of the elliptic curve cryptography depends on the elliptic curve discrete logarithm problems. So now, but still, this depends on the complexity of the hard math problems. If someone solves the math hard problems, what problem will happen? Because tomorrow someone comes with a solution for prime factorization problem. Yes.
Sir, can you please
describe
the difference between prime factorization problem and elliptic curve discrete, sir?
So prime factorization problem, you see that. So in normal, in RSA crypto systems, we are using a very big prime numbers. Got my points? Very big prime numbers. If someone can factor the big prime number into two prime numbers, got my point? Two prime numbers, then he can easily compute the decryption key of the RSA cryptography. Got my point? But if the number is, suppose I am using 35. So can you factorize 35 into prime numbers? So one is 7 into 5. Am I correct? 7 and 5 are the prime numbers. Am I correct? If you understood. So similarly, discrete logarithm problems. So discrete logarithm problems, suppose 2 to the power a is given. 2 to the power a is equal to 8. Suppose 2 to the power a is equal to 8. So what is a? Can you tell? What is a? 2 to the power a is equal to 8. What is a? A is equal to 3 definitely. Got my point? If somebody is given you
3, sir. 2 cube. Yes, sir.
Somebody is given you 8, it tells you to find a, then you have to solve the discrete logarithm problems. That's